A subsequence is exactly what it sounds like. From an original sequence, we select some terms and we leave out some other terms, but in this process we need to make sure that, first of all, we end up with a sequence, so we need to end up with an infinite number of terms, and we also need to make sure we don't mess up the order, so there is still a connection between my original sequence and my new subsequence. But we're going to give a definition, a more formal definition later on. But before that, let's take a look at some examples that will give us an insight of why we care about subsequences. We already know that if a sequence is convergent, then it is bounded. And we also saw some examples of sequences that were bounded but not convergent, like the -1 to the n that goes up and down, up and down. So to fix this problem, we called the monotonicity theorem. And then we say, okay, if I know that my sequence is bounded but also monotone, then I can make it be convergent. And that was the monotone convergence theorem. It tells me that monotone and bounded implies convergent. Okay, is there anything else that I can say about bounded sequences that could be nice, could be useful? The answer is yes, we can extract quite good information about bounded sequences, but we'll have to, wait a bit to formulate a proper theorem about it, but let's take a look at an example first. Consider our old friend, the sequence -1 to the n. It's bounded, and we know it's not convergent because it oscillates, but we can see that it's quite predictable. It is very nice as a sequence, we can see nice patterns. If I only focus on the dots at the top, we can see that they converge. Actually, it's a constant sequence if we just look at it as like those blue dots. If I only look at the dots at the bottom, again, this looks like a convergent sequence. It's a constant sequence. So, you see, if I'm only focusing on the even terms of my sequence, all of them are equal to 1, so that will converge to 1. And if I only look at the odd terms of my sequence, all the terms are equal to -1, so that converges to -1. So here we have a bounded sequence that is not convergent, but it was able to extract some bits, right, that became also a new sequence in itself that was convergent, and then a different one that was convergent, but convergent to a different limit. And that is going to be actually very important, because later we're going to see that if someone gives to me a bounded sequence, no matter what it is, if I know it's bounded, I will be able to always find a convergent subsequence. In this case, it was very easy to do. We just had to look at it. We look at the dots at the top, the dots at the bottom. Easy. 2 convergent subsequences. For journal sequences, it's not as easy, but that theorem is going to tell us that whenever we have a bounded sequence, we can always find a convergent subsequence. But before we all work on those things that are, very formal and a bit complicated, let's give ourselves a formal definition of subsequence. So far, we only have an intuitive idea. Okay, a subsequence is, to begin with, a sequence, and each term of my new sequence, Bn, is going to define the following way. Bn is equal to A of Jn, where, like these J's, J1, J2, and so on, is strictly increasing sequence of natural numbers. The reason why I ask to be a strictly increasing sequence of natural numbers is because we don't want to mess up the order. Remember what I said earlier? So this will guarantee that the terms of my subsequence come in the same order as they came in my original sequence. And we're just picking out some of them. And let's take a look at an example. For example, if we have our famous sequence -1 to the n, well, if we take the even terms, then we're just looking at the a sub 2n, which is -1 to the 2n, which is 1. And the odd terms are the a sub 2n plus 1. These are -1 to the 2n plus 1. This is -1. So those are the terms of those sequences. And now what happens if I look at this one? So I look at this term 1 over n, and I'm going to look at my strictly increasing sequence of jn's. It's going to be 2 to the n. So then I'm going to be only interested in terms of a form like b sub 2 to the n, which means we're only looking at terms of the form 1 over 2 to the n. And here I have the terms of my original sequence 1 over n, and then I'm highlighting in yellow the ones that I'm picking out, right? These are the ones of the form 1 over a power of 2. And that is the idea of a subsequence. It's not really that complicated. Now, there's something natural to think is, okay, what would be the limit of a convergent subsequence? Well, if I know that a sequence converges to L, the subsequence should have the same properties as my original sequence, so I want my subsequence to also converge to L. And this is true, and that's what we're going to prove. Well, to prove it, we need to fix an epsilon positive. Now we know that an converges to L, so there exists an n naught, such that if n is bigger than a naught, then the distance between an and L is less than epsilon. Okay. And now I have a claim here. For now, believe me, I'm going to prove it later. But what I'm going to say is that if I have strictly increasing sequence of natural numbers, Jn, then Jn is greater than or equal to n for all natural numbers n. It feels obvious, but we need to prove it. Okay, if I assume that this claim is true, then if I pick an n bigger than n naught, by the previous claim, we know that Jn is greater than or equal to n, so it's strictly bigger than n naught. But then that would mean that a sub Jn minus L in absolute value is less than epsilon, and that completes the proof. Well, sort of. It completes the proof if I actually believe my claim, so let's try to prove the claim. Well, we're going to prove it by induction. The base case is very simple. We know that J1 is a natural number, so it has to be greater than or equal to 1. Good. Now we're going to assume that Jn is greater than or equal to n, and remember we need to show that Jn plus 1 is greater than or equal to n plus 1. Okay, remember that my sequence is a strictly increasing sequence, and this is very important because that tells me that Jn plus 1 is strictly greater than Jn, which is greater than or equal to n. But now, Jn plus 1 is strictly bigger than n and is a natural number, so it has to be bigger than or equal to n plus 1, and that completes the proof of my claim. Some important consequences of this is, remember what I told you in the previous video, that the limit of the sequence an plus 1 was the same as the limit of the sequence an, because we are shifting things by 1 a little bit. That's an immediate consequence of this theorem because, well, the an plus 1 is a subsequence of the an. And indeed, if I just shift my sequence by a finite number of terms, I just push it, the limit would still be the same. And now I want to take a look at something that is also a consequence of this, that is a bit more difficult to see, so I'm going to go slowly. This, we want to look at the contrapositive of the statement that if my sequence converges, then all the subsequences converge to the same thing. I invite you to pause the video here and try to think about how we could write down the contrapositive before we continue. Welcome back. So, the statement is saying the following, that if a sequence converges somehow, then all subsequences converge and all convergent subsequences converge to the same limit. Now here I'm expanding it to make it a bit easier to see. So that is actually what the theorem is telling me. Okay, so I know that the sequence converges and all the subsequences converge and converge to the same limit. So what is the negation of all subsequences converge and all convergent sequences converge to the same limit? Well, we have an and here, So it would be that either there is a subsequence that doesn't converge, or that not all the subsequences converge to the same limit. Now, those two possibilities here. So, to build a contrapositive, what I would say is that, well, if a sequence either has a subsequence that diverges, or it has two convergent subsequences that converge to different limits, then my original sequence is divergent. So if you're struggling to prove that a sequence is divergent, for example, you can try to look at subsequences and see, maybe you find two subsequences with different limits, or maybe you find that a subsequence is divergent. Maybe that's easier to prove. And that will tell you, using the contrapositive of the previous statement, that your sequence has to be divergent. And this is very useful, so try to keep in mind.